Dear students, hello. In this video, we're going to work through 3 exercises related to the continuity of a real valued function. Exercise 1. Sketch the graph and study the discontinuities of the function. f of x is defined as the fraction with a numerator of 2 times x squared minus 5 times x minus 3 and a denominator of x squared minus 4 times x plus 3. Exercise 2. Determine the real value of k that makes the function continuous over all real numbers. f of x is a piecewise defined function. 2 times x squared plus 4 times x is greater than or equal to 1. Negative x plus k if x is strictly less than 1. Exercise 3. Study the continuity of the following function. f of x is a piecewise defined function. X times the sine of 1 over x if x is different from 0 equal to 1. If x is equal to 0. Exercise 1. Alright, today we're going to tackle a rational function. Just the name sounds intimidating. But don't worry, we're going to break it all down calmly. The function is called f of x, and it's defined by a fraction involving polynomials. On top, in the numerator, you've got 2x squared minus 5x minus 3. On the bottom in the denominator, you've got x squared minus 4x plus 3. What we want first is to find out for which values of x the function is defined. Why? Because you're not allowed to divide 0. So we take the denominator and say x squared minus 4x plus 3 not equal to 0. Alright, let's bring out the discriminant. Remember, delta is b squared minus 4 times a times c. Here, a is 1, b is minus 4, and c is 3. We calculate minus 4 squared is 16. Then minus 4 times 1 times 3 is 12. So 16 minus 12 gives delta equals 4. Right. That means we have 2 roots. We use the magic formula and find x equals 1 and x equals 3. So f of x is not defined at 1 or 3. Those 2 values are for. Next, we want to simplify the function. To do that, we'll factor the numerator. Let's go back. 2x squared minus 5x minus 3, and once again, we compute a discriminant. A is 2, b is minus 5, c is minus 3. Delta, minus 5 squared is 25, and minus 4 times 2 times minus 3 is plus 24. So delta is 49. We find the roots. X equals minus 1/2 and x equals 3. So, factorizing the numerator gives 2x plus 1 times x minus 3. We do the same for the denominator. It factorizes to x minus 1 times x minus 3. And there it is. The factor x minus 3 appears in both numerator and denominator. We simplify it. The function then becomes 2x plus 1 over x minus 1, but careful. X must still not equal 1 or 3. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. The numerator in a different way to better understand the behavior of the function. 2x plus 1 is the same as 2 times x minus 1 plus 3. Why? Because 2 times x minus 1 gives 2x minus 2, and if you add 3, you get back to 2x plus 1. So now, f of x becomes the sum of 2 plus 3 divided by x minus 1. At this point, we can make a graphical connection. This function resembles a transformation of the function g of x equals 1 over x. You can get the graph of f from that of g by applying a translation, that is, a shift, by a vector with coordinates 1 and 2, and then multiplying by 3. Now, let's focus on the point x equals 1. We'll study the limit of f of x as x approaches 1, first from the left, then from the right. We have the sum of 2 plus 3 divided by x minus 1. When x approaches 1 from the left, the denominator x minus 1 is slightly negative. So 3 over something very small and negative gives a very large negative value. Thus, the limit tends toward minus infinity. On the other hand, when x approaches 1 from the right, x minus 1 becomes positive, very small. So 3 divided by that small positive number gives a large positive value. The limit, this time, tends toward plus infinity. And there it is, a clear asymmetry between the two sides. The point x equals 1 is a discontinuity of the second kind, also called an essential discontinuity. That means the function blows up on both sides of the point, but in opposite directions. Exercise 2. The function f of x is continuous over all real numbers, except possibly at one particular value, when x approaches 1. Now let's ask ourselves a real question. What happens in the neighborhood of this value? More precisely, is the function continuous at x equals 1? To answer that, we need to examine the left-hand and right-hand limits of 1 and make sure they match the exact value of the function at that point. Let's start with what the function actually equals when x is exactly 1. We're given that the function equals 6 when x is 1. Now let's focus on the limit of the function as x approaches 1 from the left. That means using the expression for the function that applies to values strictly less than 1. Here we have negative x plus a constant, which we'll call k. Now let's compute the limit of negative x plus the constant k as x approaches 1 from the left. Substituting 1, we get k minus 1. Now let's move to the right side. For values strictly greater than 1, the function is given by a polynomial, 2 times x squared plus 4 times x. So let's compute the limit of 2 times x squared plus 4 times x as x approaches 1 from the right. Substituting 1 squared is 1, times 2 gives 2, and 4 times 1 gives 4. Adding them together, we get 6. Now, for the function to be continuous, the left-hand limit must equal the right-hand limit, and both must be equal to the exact function value at this point. In other words, we need the constant k minus 1 equals 6. Solving for k, we find the constant k equals 7. Exercise 3. Alright, imagine a function that's pretty quirky. It's well-defined everywhere, except at 0. It's just doing its thing. But at 0, it gets a little weird. Here's the setup. We take a function f, which, for any x other than 0, is given by x times the sine of 1 over x. Sounds wild, right? You take x, flip it, find the sine of that, and multiply by x. It's like a mathematical roller coaster. Now, what we really want to know is, what happens as x approaches 0? Let's notice something interesting. The sine function always swings between -1 and 1. That's its thing. No matter what happens with 1 over x, the sine of that is still locked between -1 and 1. Here's where the magic happens. If sine is trapped between -1 and 1, then multiplying it by x means the result is stuck between -x and x, or the reverse, depending on the sign of x. And what does that mean? We can use the squeeze theorem, which tells us that as x approaches 0, our function must also approach 0. Beautiful, clean, precise. But wait, there's a twist. When we actually check the function's value at x equals 0, it's not 0, it's 1. And that changes everything. The function is not continuous at this specific point. Why? Because the limit is 0, but the actual function value is 1. It's like expecting calm and getting fireworks instead. Dear students, thank you for watching the video until the end. Next time, I'll say goodbye to you.